Welcome students to your first lecture on online video lecturing session this semester. I will be teaching you refrigeration and air conditioning ME 403 for third year mechanical engineering batch 2017 and 18. The prerequisite for the course is thermodynamics and fluid mechanics 1. The textbook for the course, the CLO, there are 3 CLOs in this course. In fact it's 4, but the 4th one was for practicing of the basic thermodynamic concept for refrigeration cycles, and then psychometric calculations and cooling load estimations is CLO2, and CLO3 is the air conditioning systems types and applications, and the air distribution systems or duct design, etc. So there is further details of CLO1s are here. Refrigeration cycle, CLO1 is refrigeration cycle, and types of refrigerants and application of refrigeration, and so those are the CLO1, CLO2, CLO3. So refrigeration by definition is the process of removing heat from a lower temperature region to a higher temperature region. So as you know, the heat always travels from high temperature to low temperature, but in refrigeration the reverse happens, because this is based on the reversed Carnot cycle with air conditioning. So with reference to refrigeration, we have two different types of devices. We call it refrigerators and heat pumps. Basically they are the same device, but their objectives are different. As you can see in this figure here, a refrigerator or a vapor compression refrigeration cycle is basically consisting of 4 devices, starting from a compressor, a condenser, an expansion valve, and an evaporator, and expansion valve, and then we have liquid in the condenser and the expansion valve, and we have vapor in the evaporator and the compressor. So it's a two-phase system. We also call it's a two pressure system, one high pressure, one low pressure. So high pressure is in the condenser and low pressure is in the evaporator. The pressure range is like in the condenser it will be somewhere around 800 kilopascal to 1000 kilopascal, whereas in the evaporator it will be somewhere around 120 kilopascal, 100 to 120 kilopascal. So as you can see, the evaporator, the low side pressure, and the condenser, the high side pressure, the difference is about 10 times. They are different from each other. So in the refrigerant that we are normally using here is R134, and the other ones are R22, normally, or R11 are the different types of refrigerant that we use in a refrigerator or a heat pump. The objective of a refrigerator is to keep a cooler place colder, and the objective of a heat pump is to keep a warmer place warmer. So they are different in their objective, but they are basically the same equipment. For example, if you have a refrigerator, then the freezer box temperature is somewhere around -15 to -25 degrees centigrade, whereas the kitchen atmosphere where the refrigerator is placed is about 30 degrees centigrade. So what the refrigerator cycle is doing is it is absorbing the heat from the freezer box and throwing it into the kitchen atmosphere, which is at a high temperature. So it is moving heat from low temperature to high temperature. So in case of a heat pump, the example for the heat pump is that of a heated room in a winter season, when the weather outside is 0 degree or negative temperature outside, like -10 degree maybe, and inside your room you want to be comfortable, so your temperature inside the room is 20-22 degrees centigrade. So what we are doing, that we are extracting heat from the outside winter condition and transferring it to the inside of the room. So again we are moving the heat in the opposite direction than it naturally does, but the objective is different. In case of a refrigerator, freezer box had to be kept cooler. In case of the winter season room, we want to keep the room cooler, so we are transferring heat in opposite direction. Basically, both refrigerator and heat pump are the same device. You can use your window AC air conditioner as a refrigerator, or as an air conditioner, or as a heat pump, both at the same time. When you use it in the right order, then it acts as air conditioner. A refrigerator is a cyclic device which transfers heat from a low temperature region to high temperature. The working fluid used in the refrigerator cycles are called refrigerants. QL is the amount of heat which is being removed from the low temperature surrounding, or from the low temperature medium, TL, and QH is the magnitude of heat that is rejected to the warm space at temperature TH, and W net in is the net amount of work required by the compressor. So this is the input energy that we have to supply in order to move heat from a low temperature to a high temperature medium. The efficiency of a refrigerator is expressed in terms of the coefficient of performance, denoted by COPR. COPR is somewhat similar to efficiency of a heat engine, but the difference is the efficiency of the heat engine can never be 1 or greater than 1, but in case of a refrigerator or a heat pump, the coefficient of performance can be greater than 1. That is why we don't use efficiency, the term efficiency, for the refrigerator or heat pump. We rather use coefficient of performance, COP. So by definition, COPR, that is coefficient of performance for a refrigerator, is desired output divided by the required input. The desired output here is, of course, to move heat from the freezer box to the kitchen atmosphere. So the amount of heat which will be removed from the freezer box is QL, from the low temperature medium, L denoting low temperature, divided by the work required by the compressor, W net in. And if you do energy balance for a closed system, you can prove that the net work is equal to QH minus QL. You must have done it in your thermodynamics course, so you can go and look it up. So QL divided by QH minus QL. Notice that COPHP is again desired output divided by the required input. Required input is still the same, that is the work required by the compressor, but the desired output is the QH. Now we want to transfer heat into the high temperature room, so QH. So COP of heat pump is equal to COPR plus 1, that is COP of heat pump will always be greater than COP of the refrigerator. Now, as I said in the beginning, the refrigerating system is basically based on the Carnot cycle, or we say Carnot reverse cycle. Carnot cycle we study for the heat engine, and then because we say it is comprising of two ideal adiabatic process and two isothermal process. So it's an ideal process, and ideal process can be reversed. So when we reverse it, the heat engine becomes a refrigerator cycle. So Carnot cycle is a completely reversible cycle operating between a constant temperature heat source and heat sink. So it's operating between the two temperature limit. One is the low temperature, we call it heat sink or heat sink, and the other one is the high temperature, we call it heat source. For the reversible process, as you can see in the diagram, this is the diagram between temperature and the entropy. So 1 to 2 is the isentropic compression, which is normally occurring in the compressor. 2 to 3 is the isothermal heat rejection in the condenser, and 3 to 4 is the isentropic expansion process in the expansion valve. This is an ideal situation. We are discussing Carnot cycle here. So in Carnot cycle 3 to 4, the expansion process is an isentropic process, ideal process. Okay, and then 4 to 1 is the isothermal heat addition in the evaporator. So that's the complete cycle for Carnot refrigeration. So by definition, because it is an ideal cycle, so ideal cycle means it is a reversible one. So the amount of heat transferred to the system, and if the same amount of heat transferred back from the system will become in the same state without any traces of any change, because it's an ideal process. Because of that, we consider that the heat transfer to the system and heat transfer out of the system, the ratio of the two heat transfer should be equal to the ratio of the absolute temperature when we are transferring the heat and when we are rejecting the heat from it. So that because of that reason, we say we can replace what was in COP, that what we had used Q, that is the amount of heat transferred by temperature T. So COP Carnot will be equal to TL divided by TH minus TL, and COP Carnot will be TH divided by TH minus TL. So the denominator is same, just the numerator is changing depending on whether it is a COP-R or COP-HP. These are the best COP can be achieved by the Carnot cycle only, Carnot refrigeration cycle only. All actual refrigerators and heat pumps operating between these temperature limits have lower coefficients of performance, and the reason is obvious, because here we are considering all the processes to be ideal processes, so they can move forward and come backward without leaving any traces on the system. But the same is not true in our actual cases. In actual cases, when we move forward from one state to another state, and when we come back, the state doesn't come back exactly at the same state as it was before. There will be some traces left. So in that case, there will be some losses in the actual cases as compared to the ideal case. So that's why we say the Carnot efficiency, the Carnot COP will always be higher than the actual one. High COP, our two temperature limit, one is the cold room, one is the atmosphere, 253.15 and 303. These are the two temperature limits that we want to operate. But in order to have a heat transfer, we need a temperature difference. So we have to go slightly higher on the high temperature side and slightly lower on the low temperature side, so that we can have a heat transfer. Otherwise there will be no heat transfer, and then but that is also restricted by equipment size and cost. As I have been explaining to you in your thermodynamics course, if in case of, if you look up the actual Carnot cycle here, the heat transfer in the condenser or heat transfer in the evaporator, they are at the constant temperature. The line is horizontal here at the same temperature. As we know it, for heat to transfer from one state to the other state, from one point to the other state, there is a temperature difference required. Otherwise there will be no heat transfer. But ideally it can be. In actual case it cannot be done. In ideal situation, does it really happen? As I have been giving you examples of condensation and evaporation occurring in the atmosphere, in the nature. So when you place a pot of water in a room, the temperature of the water in the pot and the temperature of the air in the room will be the same. But after some time you see that the pot has emptied, all of its water has evaporated, while the temperature remains same. So there is a condensation process going on at the same temperature. Similarly, reverse, you can think of it in the morning when you see dew formation on the leaves and on the plants, etc., on the surfaces. But the temperature basically of the surface and the air surrounding it is about the same. This can happen only when the surfaces are very, very large. In our case, in case of a refrigerator machine, we cannot have such a large surface. So we need a temperature difference. That is the reason for having a delta T. Carnot efficiency, Carnot cycle performance by using a gas refrigerator or gas as the medium in our refrigerator, and a vapor as the medium as a refrigerant in our refrigerator cycle. So when we use the gas, As you can see here, the two temperature limits are cold room temperature and the atmosphere. If you are using the gas, the gas has to be compressed or heated up slightly above the atmosphere temperature, and then it will be cooled back to the atmospheric temperature. So this X amount of energy is the extra amount of energy which is needed. Similarly, so the efficiency will be dropping here. Similarly, when we are cooling it down, it has to cool below the cold room temperature so that it can absorb some heat from the cold room and then come back to state 1, come back to the cold room temperature. Okay, so this Y area will be another loss temperature limit. So in case of a gas also, if we use a gas as a refrigerant, we cannot achieve Carnot efficiency. It will be slightly lower than that. It will be lower than the Carnot COP. If we use a vapor, so in this diagram, as you can see, this is the temperature entropy diagram. So 1 to 2 is the compression process. In the compressor, 2 to 3 is the condensation process in the condenser at a higher pressure, and 3 to 4 is the expansion process in the expansion valve or in a turbine. You can say that when you're expanding, you can expand it through a turbine, and 4 to 1 is the heat addition process into the in the evaporator. So here I would like you to pay attention on this 1 to 2 process. This is a mixture state. State 1 is a mixture state. Here we have refrigerant vapor and refrigerant liquid, both saturated vapor and saturated liquid, and we are sending it to a compressor. As we know, compressor can only handle gas medium, it cannot handle liquid medium. If we let the liquid go into the compressor, it will make it inefficient. It will try to erode the compressor parts. It will remove the lubricant from the surfaces of the piston and it will become more rough, and more heat will be transferred, so it will be damaging your compressor. So it's not a good idea to send a mixture into the compressor. So that is one of the problem in this vapor refrigerant system. And the other one is when condenser probably is okay when it can condense saturated vapor to the saturated liquid, but when the saturated liquid is expanded into the evaporator, so during this expansion process we can think of why not place some kind of expansion device that can extract some work out of it, like you have the steam engine. Similarly, we can put some kind of turbine system here, so that can extract the work from this high pressure liquid which is coming down to the low pressure vapor. But the construction and fabrication of such a turbine is more costlier than the energy we will save. So because of that, we don't use a turbine here, rather we use a simple expansion valve and does not care about the energy that we are losing here. So that's why this is not an isentropic process, this is an isenthalpic process. It doesn't, in actual case right here it is showing as an isentropic process, but in actual scenario, in actual device, it cannot be an isentropic process. It will be a irreversible process. There will be irreversibility in it, and it becomes a isenthalpic process. So if you look at the theoretically possible, but actually it is not possible. Wet compression can damage the compressor, so dry compression is required. Now about between process 3 to 4, the economics of the power device, which essentially leads to an isenthalpic expansion process. Again, the stress is an isenthalpic. It is not an isentropic process, it is an isenthalpic process. So this is an actual refrigerator consisting of the 4 familiar components of any refrigerating system, any vapor compression system, that is a compressor, a condenser, an expansion valve, and an evaporator. So process 1 to 2 for a standard is isothermal addition of heat at constant pressure. So you can see the TS diagram and the pH diagram here. We have put the diagrams here. So if you compare the two diagrams, you will see the difference between two lines. basically two lines. You can see clearly the difference, the process 1 to 2 and the process 3 to 4. If you look it up, process 1 to 2 in TS diagram, it is a straight vertical line. This is the compression process, and we consider it to be an ideal process. So it's an isentropic compression process, so to get a vertical line. But here in the pH diagram, the constant entropy line is a curve like this one. So this 1 to 2 is become a slanted line here. The second difference is process 3 to 4. 3 to 4 is not an isentropic process, so in TS diagram it is kind of slanted. That is, the entropy is increasing. It's an irreversible process, so entropy will increase 3 to 4. But if you look it up in the pH diagram, enthalpy remains same. Enthalpy is constant. It's an isenthalpic process. So 3 to 4 is a vertical line here. So H3 is equal to H4. We will be using it more often than not. So you should always remember, as solving any cyclic problems, as you may know, you may have noticed, you have been told in your earlier courses that the basic purpose of solving any numerical for a cyclic device is to find out the enthalpy value. Let's move on. Comparison with the Carnot refrigeration cycle. The standard vapor compression refrigeration cycle introduces irreversibilities due to non-isothermal heat rejection. So that is this one. It is not at a constant temperature, process 2 to 3, and process 2 to 3 basically is not an isothermal process anymore. In ideal it was isothermal, in Carnot cycle it's an isothermal process, but in actual this is not an isothermal process. As you can see, it will go from 2 to 2 dash and then to 2 dash to 3 at temperature Tc. And then isenthalpic throttling process 3 to 4. 3 to 4 is no longer an ideal process. In Carnot cycle this is an ideal process, so it's a vertical line, but in actual it is a slanted. 3 to 4, the entropy has increased. So we have lost this much amount of energy because of that. So that's why the efficiency or the COP of the actual will always be less than the COP of the Carnot cycle. Consequently, the cooling effect reduces and the work input increases, thus reducing the system's COP. Work will increase because of this increase. The A1 is the increase in the compressor work. Actually, in Carnot cycle, it's just a vertical line from here to here, and then it goes here like a. So this is the amount of heat or extra amount of energy that will be required, and here you will be losing extra amount of energy because the process is not ideal process. So this is shaded area and this hatched area, A1 and A2, these are the losses in actual cycle as compared to the Carnot cycle. Okay, so moving on. Refrigeration effect is H1 minus H4 from the diagram. As you can know, what is the refrigeration effect, what is the cooling produced, that is H1 minus H4. And if we multiply it with the mass flow rate m dot, we can find out the total refrigerating capacity. M dot is the mass flow rate, m dot into H1 minus H4. And COPR for the refrigerator is a rate of heat transfer QL divided by rate of heat transfer QH minus rate of heat transfer QL. So m dot and m dot, because we say it's a steady flow process, so the amount of mass flowing through the entire refrigerating circuit is same, so m dot and m dot will cancel out, and we will have H1 minus H4 divided by H2 minus H1. The power in kilowatt per kilowatt of refrigeration is the inverse of COPR. This is just a formula, you have to remember it. And refrigerating efficiency is COPR divided by COPR of the Carnot. If we know the two temperature, the low temperature and the high temperature. Relevant refrigerant properties are available in either in the tabulated form or the graphical form. We have provided you with figure and tables and booklet on your drive, so you should look into that. There you will find all the refrigeration properties available either in tabulated or graphical form. Refer to tables and figures in annexures. So you should look at that in annexures. It is there for you to look between pressure and enthalpy diagram, and it is showing different properties constant line. So you can see the entropy constant line is curved line like this one, and V constant is the line like this one. So when you look at these charts, you should be able to figure out these lines, which lines is showing what. This is the saturation line, this is the saturated liquid line, this is the saturated vapor line, okay, and this is the constant temperature. This is what is the difference between the actual vapor compression cycle and the ideal one. So as you can see, actual one is so the ideal one is starting. Ideal one is basically the dash line one. Dash one is the ideal cycle. Okay, so it starts from the saturated vapor line and goes to the superheated region, and then the refrigerant will be cooled down and become saturated vapor line, and then it will expand. Okay, so that's the actual constant enthalpy process. That's the ideal one. In actuality, when we will have some superheating before your vapor enters into the compressor or at the compressor inlet, we will have some superheating, not exactly at saturated vapor line, but it will be slightly into the superheated region. So that will be one difference. And when you are cooling in the condenser, we may get some subcooling done also. So it will not be saturated liquid that we will get it, but we will get slightly subcooled liquid. This happens because of some modification also we make in the refrigerating cycle. We place a heat exchanger here also. So heat exchanger, so that we can take advantage of the coolingness which this saturated refrigerant will still have, and we want to cool down further this saturated liquid so that our efficiency can increase, so that the refrigerating capacity can increase. So for that purpose we also deploy a heat exchanger between these 2 points, between the liquid coming out from the condenser and the liquid going out from the evaporator. We transfer heat between the two. So as a result of that, we get a slightly heated superheated region at the inlet of the compressor and slightly subcooled liquid at the outlet of the condenser. So those are the in the evaporator and in the evaporator and in the condenser, we consider that the pressure will remain same, but due to the friction, due to other reasons, cycle differs. Additional effects include pressure drops across compressor suction and discharge valves, pressure drops and heat gains in the connecting piping system. So as you can see, as you can imagine, when any liquid, any fluid is traveling in a pipe, so after traveling certain distance, its pressure will drop. Why? Because of the hindrance produced by the surface of the pipe itself, and because of the viscosity of the fluid itself. So those two are the factors which will hinder the flow of the fluid inside the pipe. As a result, there should be a pressure drop. Same is true here. There will be a pressure drop, and we are showing you here why the pressure drop in the evaporator, in the condenser, in the piping system of the refrigerator. The pressure drop in the evaporator, in suction line and across the suction valve has a significant effect on system performance. It increases specific volume at suction, compression ratio and discharge temperature. All these effects lead to reduction possible. So this is an example problem. I want to go over it with you. This is a simple, straightforward problem. In this example, a plant using R134, that is the refrigerant, evaporates at 0 degree centigrade and condenses at 35 degree centigrade. The refrigeration capacity of the plant is 352 kilowatt. So this 4 to 1 H1 minus H4 multiplied by M is given as 352 kilowatt. and it operates on the ideal vapor compression cycle. Determine the following: the dryness fraction at the entry to the evaporator. So X4 we need to figure out here. Because we will know H3, because the temperature of the condenser is given, we can find out what is H3 from the table. So once we know H3, H4 is known. Once we know H4, we can find out what is the X value. So that's what we will be doing, the dryness fraction at the entry to the evaporator. The refrigeration effect, so that is this effect, H1 minus H4, the mass flow rate of the refrigerant, because we are already given the capacity, the refrigeration capacity 352, so we can figure out what is the mass flow rate from this H1 m dot H1 minus H4 is equal to 352, that is given, so we can find out what is m dot. The volumetric flow rate at the suction state, the compressor power, the rate of heat rejection at the condenser, and the COP of the plant and its refrigerating efficiency. So those are the things that we need to find out using different equations as we have discussed in the theory above. So H4 is equal to HF plus X Hg minus HF or HFG at 0 degrees centigrade. So H4 we will know from the table, from the property table of R134 in your handout. This is a copy from the same thing. Okay, so our pressure, our saturation temperature is given as 35 degrees centigrade. When you look at here, the temperature is either 35 and 36 degrees centigrade, and 35 is not available, so we have to take the average value. Either you interpolate or take the average value. So HF is 200 kilojoule per kilogram and Hg is 398.60. So these values I'm getting it from the same table, but not here, because here 0 degree is not shown. I think I might have 0 degree somewhere. This is the 0 degree there you go. At 0 degree centigrade, HF and Hg. So HF, there you go. HF and Hg. HF 200 and Hg 398 at 0 degree centigrade of the refrigerant. So from the same table you can see it right there. 0 degree centigrade, see HF and Hg. These are the two values. And this is the entropy at the entrance. Okay. So at T3 35 degrees centigrade, we are taking average of the pressure. If you look at these two pressures, so we are taking the average, taking the pressure like this. H3 is HF at 35 degrees centigrade. Again, we have to take average of 247.54 and 250.48. So we'll get 249.01. Alright, from the table. This is the table for R134 included in your handout. Okay, so you should look for the table for R134. You have a table and you have a graph also in it, which we call chart. So look at the table, you will see these two values there. Now H4 is equal to H3. Therefore, in this equation we know everything else. Okay, HF is basically H3. Okay, so we will replace all those values and we will find out what is H3 is HF at 35 degrees centigrade. That's what it is. So when we replace it, we can find out what is the X value. So H1 is Hg at 0 degrees centigrade. At 0 degrees centigrade, H1 is Hg 398.60 right there. Refrigerating effect is H1 minus H4. So H1 minus H4 will get you 149.59 kilojoules per kilogram. Alright. Refrigerating capacity QL is equal to m dot H1 minus H4. QL is given as 352 in your question, so we can find out what is the mass flow rate. So mass flow rate is 2.353 kilogram per second. D is the suction is inlet to compressor, that is state 1. where V1, what is D? We need to find out. We need to find out the volumetric flow rate at the section state. So at this state, what is the volume flow rate? V. So at the section state 1, V is equal to Vg. It's a saturated vapor at 0 degree centigrade. Is that right? Yeah, this is the evaporator, so 0 degree centigrade. The evaporator is at 0 degree centigrade. So 0 degree centigrade. At 0 degree centigrade, Vg is, I haven't shown it here, but you can see in the same table, the value is 0.06931 meter cube per kilogram. So volume flow rate V dot is V1 multiplied by m dot. M dot we already figured out. So V dot, the volumetric flow rate at the inlet of the compressor, is 0.1631 meter cube per second. Now find out E. What is E? E is the compressor power. How much power required by the compressor? So that is H2 minus H1 is the amount of energy required by the compressor multiplied by the m dot, the mass flow rate. So that will give you the compressor power. So how to find out H1 and H2? H1 is fairly easy. You can say saturated condition. You can look it up, the saturated vapor from the table, and take that value at 0 degree centigrade, saturated vapor at 0 degree centigrade, which is 398. So we know that one. But H2 is in the superheated region. So how we will find out H2? For isentropic compression, S2 is equal to S1 is equal to Sg at 0 degree centigrade. So we know that because it is an isentropic process, so the entropy of point 1 is equal to entropy at point 2. We want to find out what is the enthalpy at point 2. We will find out what is the entropy at point 1, and we'll say, okay, the same is the entropy at point 2. And then we will use that one and the temperature that we know here, 35 degrees centigrade, to find out what is the enthalpy. So that's the idea. So, and here you go. What we are doing here is we figure out, we know the entropy now is this much. P2 is equal to P3, 0.88724. P3 is at 35 degrees centigrade. We didn't have 35, so we took the average, so 0.88274 here. That's it. That's the one we are using here, 0.88274. The values in superheated table are higher or lower pressures. So if you look up the superheated table, we will not find this pressure there. The pressure is either higher or lower. So we need to do interpolation. So we have in the table, we have a pressure of 1 megapascal or 0.8 megapascal, and we have to interpolate between these two to figure out what is the value at 0.88. So we will be doing double interpolation, and the arrow is showing the value that we are going to use. This is the entropy. Our main entropy is this one, so this will be in the middle of these two. This one will be middle in these two, and then we will be using these enthalpy values at these two pressure, and then find out what is these enthalpy values at this pressure. Okay, here you go. Here is the idea. First interpolation at state at P pressure 1 megapascal, and the second one at pressure 0.8 megapascal. So from the table we look it up, but for 1 megapascal the value is the entropy value is this much and this much, and then we have this value for which we don't know the enthalpy, and then we have 1.74 at 1 megapascal. We are looking at the entropy value of 1.71, 1.74. These two values are in the table, so we've copied enthalpy there, and this value is where this is the entropy value that we have. We want to figure out what is the enthalpy at this one, so this X amount will be interpolated, so we can find out that this will be by doing the interpolation we'll get this value as 424.19. Similarly for 0.8 megapascal, look at the table, so find out the entropy before and after our given entropy and the corresponding enthalpies, and then find out what is using the interpolation formula, find out what is the enthalpy here. Okay. So now we know the values at 1 and 0.8. We want to find out the value at 0.88724 in our pressure. So we entropy value and enthalpy value at 1 and 8 are copied here. And then at this one we know the entropy is this much, enthalpy we need to figure out. So the enthalpy we figure it out again using the entropy formula. So we will find out here that H2 is equal to 421.54. Okay, and then once we know what is H2, we can find out what is the compressor work. So compressor work will be 54. Again, what is the entropy equations? As I've been telling you, you can use the slope method or the other methods that we have discussed of finding out of doing interpolation, linear interpolation. So I hope you remember. If don't, then please look and go back to your thermodynamics course and look up there how to do the interpolation, formula for the interpolation. Okay. If you still don't know, I can still help you with that. I will provide you some material on that, or your same slide that I have been using it for thermodynamics. I'll provide it to you. You can see it. Again, moving on. So that is alternatively, if you don't want to do interpolation, you have to use the chart to find out what is the H2. So how to use the chart? Here's the diagram. Here's the chart for R134. So here we know that our given entropy, the entropy that we know is 1.72. So this blue line I have drawn approximately at 1.72. And then I have one pressure at 0 degree and one pressure at 35 degree. This is the evaporator line. The red one is the evaporator line and the green line is the condenser line. These are the two pressure lines. Okay, close to the two temperatures, if you can see that. Alright, so this is the condenser line. So the constant entropy will cross your condenser pressure. Wherever it crosses your condenser pressure, that is your point 2. We want to find out what is the entropy at that point, or what is the enthalpy at that point. So this entropy line is going from here and it is crossing your condenser temperature, condenser pressure line right here. So we look up what is the enthalpy here. So it is between 400 and 450, and you see the number of lines here. You divide it equally and then you figure out how much the value will be here. So it will be somewhere around 420, 425. It looks like in the center, but it is slightly less than that. So that's how you can use the chart to figure out. So we have taken H2 as 421. It's approximately right. So you can either do the double interpolation or you can use the chart to figure that out. Okay. Read the value H2 from the chart. QH is the amount of heat ejected in the condenser, which is H2 minus H3 multiplied by the mass flow rate is 406. COPR, QL divided by WC, it is 6.52, and COPR for the Carnot is TH minus TL. We know the condenser temperature, we know the evaporator temperature, absolute temperature we use. So 0 degree was the temperature of the evaporator and 35 for the condenser, but plus 273, add 273 to it, so we will get 7.80. So as you can compare the two COPs, the COPR is 6.52 and COPR Carnot is 7.8, so it should be like that. The Carnot efficient COP should be higher than the actual one, so it is. So our calculation is correct. The refrigeration efficiency is simply the ratio of the COPR and the COPR Carnot, which is 83.6%. I hope you understand. If there is any question and queries, you can write it down. We have the slide number here and everything, so you can ask me on this slide number, and this is the question. So I will try to explain you on our live session or through the email, or I probably am going to use the WhatsApp also, so on the WhatsApp. Thank you very much. We will see you again in the next lecture. Assalamu alaikum.